Hello, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion. We're talking about Einstein's theory of relativity. The topic at hand is the relativistic addition of velocities. You might remember in my last lecture, we talked about how to add velocities in a way that is consistent with Einstein's theory of relativity. In this short lecture, what I'd like to do is just go through one more quick example, and then in my next lecture, I'll get into relativistic mass and energy. So let's just do an example problem. Let's suppose now that we want to know what the speed of light is as measured by two different observers. Let's first consider one observer who is measuring the speed of light, and here's a twist on this problem. This light will travel not in a vacuum, but it will travel in a fiber optic cable. So here's a fiber optic cable, like what is used for telecommunications nowadays. And let's suppose that there was someone who is at rest with respect to this fiber optic cable. Okay, so I'm just going to draw someone like sitting on the fiber optic cable. Okay, so here you have this person who is sitting on this fiber optic cable. Okay, there we go. And he has some kind of light emitting diode or other source of light that sends light down this cable. Okay, so here is a light beam traveling down the cable. Now, here is the twist, is that we've been dealing with light traveling in vacua, or a vacuum, up until this point. But as I mentioned in one of my previous lectures, the speed of light in a vacuum, while it is 3 × 10⁸ meters per second, if one is not in a vacuum, the speed of light will be somewhat slower. So the velocity of light in some medium is going to be equal to the speed of light in a vacuum divided by what's called the refractive index. The refractive index of the medium. And this really is just a quantity that one assigns to the medium that gives you the right speed of light in that medium. So this is the velocity of light in a medium. Okay, so velocity of light in a medium with refractive index, or index of refraction, refractive index n. And in fiber optic cable, the refractive index in a fiber optic cable is about 1.5 or 3/2. It's a dimensionless quantity. So notice that that implies that the velocity of this light in this medium is going to be 2/3 c, or about 200,000 kilometers per second, because in a vacuum it's 300,000 kilometers per second. Okay, so there's nothing too controversial here. I'm just introducing the notion of refractive index and how that modifies the speed of light. We haven't done any relativity yet. Okay, now let's suppose that this fiber optic cable and this person who's on top of it are flying forward in space compared to another observer. So now what I'm going to do is I'm going to say, suppose that this fiber optic cable itself is moving at a speed u compared to another observer who's sitting here in the laboratory. Okay, so this might be like a little gnome who's riding on this fiber optic cable, and this is someone who's watching the gnome and the fiber optic cable rush past with the light traveling through it. And the question I want to ask is, what is the speed of the light? What is the speed of the light in the cable as measured by the observer who sees the cable rushing past at speed u? Okay, this might seem like a little bit of a fanciful example, but Einstein was considering an experiment very similar to this that was carried out by a man named Fizeau, who was watching not a gnome riding on a fiber optic cable with light inside, but rather light traveling through water, and the water was flowing through a pipe at high speed. Okay, so it's a similar example, and that was one of the experiments that seemed to support early on Einstein's theory of relativity. Okay, so how do we answer this question? Well, as you might imagine, we're going to have to go back and use our relativistic velocity addition formula. So let me remind you what that is. The speed of object 1 compared to object 3 is the speed of object 1 compared to object 2 plus the speed of object 2 compared to object 3 divided by 1 plus u12 times u13 over c squared. And now all we need to do is identify these various mathematical symbols with people or objects in this example. So u12 would be the speed of the light as measured by the gnome, and that would be c over n, or I say the velocity of the light in the medium. What about u23? That would be the speed of the gnome compared to this guy over here. Okay, so that would be u. And then you'd have 1 plus u12, oops, let me go back, Vm plus u, oops, Vm times u, sorry about that, Vm times u over c squared. And let's use some numbers here. Let's suppose u was equal to, I don't know, 3/4 c. Okay, so this cable is moving past at high speed, and the velocity of the light is 2/3 c. So let's go ahead and plug these numbers in. So 2/3 c plus 3/4 c over 1 plus 2/3 c times 3/4 c over c squared. Okay, what's 2/3 and 3/4? Well, let's make a common denominator of 12, so that'd be what, 8/12 c plus, let's say 9/12 c, sorry, divided by 1 plus 2/3 times 3/4 would be 2/4 or 1/2 c squared over c squared. So we have 17 over 12c in the numerator and 1.5 c, which would, c squareds cancel, so that'd be 3/2 c. Oops, I keep doing that. That's not correct. 3/2 because the c is canceled out. And so we have 17 over 12 times 2 over 3c, or this isn't going to work out really nicely. Let's compare that to 6. So 17 over 18c. So there we have it. So whereas the gnome who's watching the light travel through the cable sees the light traveling at 2/3 the speed of light, the person who is in the laboratory watching the cable rush by will see the light traveling at 17/18 the speed of light. So very near, but slightly less than the speed of light. Okay. Notice that if we had used the traditional velocity addition formula, which is inconsistent with Einstein's theory of relativity, we would have simply added the 2/3 c and the 3/4 c to get 17/12 c, which would imply that the light is traveling faster than 300,000 kilometers per second. So once again, this velocity addition formula maintains this rule that nothing can go faster than the speed of light in a vacuum. Okay, I'll stop there, and next time I will talk about relativistic mass and energy.